So remember where we left off the model of the atom. It was really the Bohr quantized orbits, and we had said that the orbits were quantized because of the wave nature of the electron. I'm trying to draw an electron that, well, I didn't quite make it match up, but pretend it does. And it's the radii that allow for the electron to constructively interfere with itself. Those are the ones that are allowed, and then where it destructively interferes with itself, it's not allowed. And so then there's a range of radii. Well, I guess no, that's not quite right. But then when we add Heisenberg's uncertainty relationship, right? So now we're saying, well, it's this kind of wave-like thing that's at a certain radius. But Heisenberg's uncertainty relationship tells us that we can't be at a certain radius, that there's some fuzziness, some blurriness to where that radius is. And it actually comes down to the quantum mechanical interpretation, or Schrodinger's interpretation of the particle, of the electron wave function, as being a probability. That there's only a certain probability that we'll find a particle at a certain position. And so due to this fact that the wave function, which is coming up next, that's what's coming up next, is a certain probability of finding the particle in a certain place, that we cannot say that the particle is in a certain orbit or is in a certain place in the atom. The particle being the electron, the electron. The electron is not found at a radius, but it has a certain probability of being found anywhere in the atom. Higher probability it's in the allowed orbits, and a lower probability elsewhere. And so that brings you to the idea of the electron cloud, that the electron might be somewhere in a certain range, but we can't say where it is at any certain time. Certainly Heisenberg's uncertainty relationship tells us we can't say where it is at any certain time, but it's also this concept of that we're going to get to next, of the wave function representing the particle of the electron is actually a probability function, and only gives you a certain probability that the electron will be at a certain radius or within a certain range of positions. So this is excuse me, this is an image where you can see that the electron can be anywhere in this sort of region here, or this region here. We can't say exactly where it is. Interesting interpretation. Again, I haven't really talked about the probability function yet. That's next. But the fact that we describe the electron by wave function, which is a probability, tells us that there's actually a finite probability of the electron being almost anywhere. It may just be small. So, for example, in reality, and this is what you're going to learn about in quantum mechanics. I'm just going to talk about this right now. Let's just say you literally have a wall and you have an electron. That electron is represented by a wave function. And we are going to, in an example soon, going to represent it by just a plane wave, a single frequency sine wave. When that wave function gets to the wall, it just gets, if it's not an infinitely, if the wall itself is not an infinite potential, meaning that there's that U is not infinity, which it generally isn't, there is a finite probability that the electron can be found in the wall. The probability goes to zero quite quickly when you get within the confines of the wall. It goes to zero quite quickly. But the wave function does have, as long as the potential is not equal to infinity, which it isn't, then there is a finite probability that the electron can be found within the wall. And that means that if the wall is thin enough, let's just make it a thinner wall, the electron can actually pass through a wall. Again, as long as the potential is not infinity, which it isn't, so the wave, oh, my iPad keeps messing up, but so the wave function is going to get smaller, but there's a finite probability that it can be found in the wall, and that means that there's a finite probability that it can move through the wall. This is absolutely true. It's absolutely correct that there's a finite probability that electrons can pass through matter. And indeed, it is the property that is used in order to create a scanning tunneling microscope. This is called tunneling. When an electron passes through a potential barrier, it's called tunneling. When it does this, right, that's tunneling. And the scanning tunneling microscope, or the STM, or the electron microscope, uses exactly that property. It says that there's a certain probability of tunneling through a potential barrier, and it uses that fact in order to map a surface scanning tunneling microscope. Let me find an image. The famous image here of a scanning tunneling microscope that is actually looking at it's a famous example. This is just a famous example here of using a scanning tunneling microscope. One of the earlier STM photographs of, I believe this is a ring of iron atoms, and it's actually able to. You can use the scanning tunneling microscope to see single atoms. And what's really cool about this picture is that what you see is that is within the ring of atoms is the electron wave, the electron wave function, the probability wave of the electron. It's showing the wave-like properties of the electron. There is an electron in there somewhere, and the wave-like properties of the electron. I can't really explain this image, but this is a STM image, which STM is a really a kind of amazing technology that allows you to image things much, much smaller than the typical optical microscopes. I always like to say that this means that if there's a certain probability that an electron can pass through a wall, then there's a certain probability that you can pass through a wall. So that means that, just because it's a pretty low probability, you've got to try it a lot of times. So you should spend all day walking into doors and seeing if you can pass through. Or the next time you walk into a door, tell people around you who look at you and look at you funny, just say, hey, you were just testing quantum mechanics to see if you could tunnel through the door. There is a certain probability that you can tunnel through the door. There really is. But that probability is so low that, sorry, it'll never happen. Because while there is a finite probability of a single electron passing through the door, you are made up of a lot of electrons. And when I say a lot, I mean, an unimaginably large number of electrons and other particles. And each of those particles has to choose to tunnel at the same time. So the probability, let's say the probability was, I don't know, I mean, it's a small probability of a single electron is 0.1 that you're going to tunnel, that electron's going to tunnel through the door. Then you got to take 0.1 to the number of electrons and particles in your body, 0.1 raised to the power of 10 to the 27th, and that gives you a probability of never being able to actually tunnel through the door, although there is a finite probability that you can do it. So if you walk into a door, you can still say you're trying it out. Okay, thought that was an interesting aside. See you later.